All right, IB students, we're here to move on into topic 2, which is about atomic structure, and topic 3 is about periodicity. So they're very well blended together, and so the notes will come all in topic 2 and topic 3. There will be two different tests, but just to let you know. So we'll begin by just kind of reviewing our history of the atom and what the IB wants you to know. And so we remember from first year chem about Dalton. John Dalton, who was the English school teacher, came up with five postulates or five things that he thought that matter was. He didn't do any science experiments. He just kind of made these things, and he turns out that he was mostly right. The only thing that he was not all right is that atoms of the same element are not alike in every way. That's because we have isotopes, and so some of them have more or less neutrons than others. So there are different numbers of neutrons. And then the first one, all matter is composed of tiny indivisible particles. Well, it is composed of tiny particles, but we learn by splitting the atom that we can divide them and get more atoms. You can split a uranium nucleus into two different other nuclei. So then we learned about J.J. Thomson and his theories into the cathode ray tube. So what he was able to do is he was able to use an electric current and with a cathode ray, which is a stream of electrons and a gas, and using a magnetic field, it was able to bend those electrons, like so. So we knew that there was some type of charge here, some type of positive or negative charge, and that's what J.J. Thomson does. But J.J. Thomson was not the person who actually really discovered the electron, though. That was the Goldstein's canal rays, which does the same type of thing, but it does these porous holes right here, and so we're able to figure out the electrons would move towards the anode, and the positive canal rays would move towards the cathode. So now. We now are up to Ernest Rutherford, and he does a gold foil experiment where he has his experimental setup where he set up a chunk of uranium inside a lead shield, and so it emits radioactive particles, it emits alpha particles, or positively charged, and he knows that they're positively charged, and he fires them at some gold foil. And what he finds is his discovery is that most particles go straight through, about 99% of them, and some of them are deflected towards the other sides, towards the sides or back towards him. They're collected all around here. So we're actually able to deduce from this and to conclude that the positive charge is not just the whole positive thing, which is what Thomson thought. The positive charge is actually a very small nucleus instead. So the positive charges were mostly going through, and seeing these arrows right there. Every now and then they would hit the nucleus and bounce back. Now James Chadwick was discovered the neutron by using beryllium and bombarding it with alpha particles again through at beryllium, and then it was caught by some paraffin wax. Now what we were able to figure out was that there were things being caught by the paraffin, but were still going through, and things that were not. So we were able to figure out that there was some type of particle that weighed just the same amount as a proton, but it did not have a charge. So, and we call those neutrons. And so that's where we're able to figure that out. And it explained why the atomic numbers weren't matching up with the atomic masses. we were starting to get neutrons in there and in the nucleus. Okay, so you should probably know this, where an atomic number is the number of protons, right? We knew that. And the atomic mass is the number of protons plus the neutrons. That's the way IB likes to say it. They call that the atomic mass or the relative atomic mass. You may have heard this as the mass number, but IB likes to call it the atomic mass. The isotope. An isotope is the same element with different numbers of neutrons. Thus, they have different mass numbers. So the same number of protons, but different numbers of neutrons. And there's two ways to write isotopes. There's either the hyphen notation here, or the isotopic notation, or nuclear notation. So hyphen notation, we'll say carbon 12. That means that it's the element carbon. It has 6 protons, but its mass number is 12. And for isotopic notation, it would be a C right here. Let's see. Get a pen. It would be a C. You would sometimes have a 6. The 6 is optional. That shows you how many protons there are. And then you would write a 12 right there. Okay, so that would be isotopic notation. So identify the subatomic particles present in an atom of radium-226. Well, we look up radium on the periodic table. We find out that it has 88 protons. So it has 88 electrons. It's a neutral atom, so it's a no positive or negative charge, and it has 138 neutrons. So 226 minus 88 is 138. You'll find that the heavier you get, the more neutrons that you start to have. You get more neutrons than protons. Now, identify the subatomic particles present in the ion calcium 2+. Well, on the periodic table, it has 20 protons, but it has 2 less electrons than it's supposed to. That's because of a 2 positive charge. It's lost 2 negative charges, so it's lost 2 electrons. So it's 18 electrons, and we cannot tell the number of neutrons from this separate here. So I would not write that. I would not question mark neutrons, but we cannot find that out yet. So identify the species with 17 protons. That would be, sorry about the gap here, chlorine, and then have a 17 on bottom, and then a 35 on top, because it has 17 protons and 18 neutrons. 17 plus 18 is 35. And then it has 18 electrons. So it has 1 more electron than it's supposed to have, so that's why it's got a negative charge right there. Good to go. State 2 physical properties other than boiling point and melting point that would differ for the 2 isotopes of chlorine. So you could have chlorine for 35 and 37. What would be different? Well, it could be density. Their masses will change. 35 and 37 will be different. So masses will change, the densities will change. The kinetic energy at a given temperature would change, and also their viscosity as well, because viscosity is dependent on mass. Kinetic energy is also dependent on mass. Okay? Good things. Boiling point and melting point are dependent on mass, but those weren't options. They're dependent on mass because of their intermolecular forces. So, example number 5. Explain why the relative atomic mass of tellurium is greater than the relative atomic mass of iodine, even though iodine has a greater atomic number. Well, tellurium has an average of more neutrons than iodine, thus providing a greater mass. Okay. So, yeah, tellurium has more neutrons than iodine. Now, when you are given a problem like this, or you're given a question where it says explain something, explain means give a detailed account. So it's basically probably going to be a statement, 1 or 2 sentences, and it's asking you to compare tellurium to iodine. So in your answer, you must write tellurium, and iodine in your answer. It has more neutrons than iodine. Okay, you must compare both of them to get credit. All right, so that's going to be it. There's a little bit of homework for this, but we'll move on. Have a great day.